Each of these bundles of uranium fuel produces enough heat to generate 1 million kilowatt-hours of electricity. But how is enriched uranium obtained? We visited the world's largest high-quality uranium deposit and a nuclear fuel factory to discover how uranium is extracted from nature and how one of the Earth's most dangerous metals is processed. Uranium is a metallic element discovered by a German chemist in 1789. The significance of this discovery was not understood until a century and a half later. In 1938, scientists discovered that uranium atoms could be split to produce energy. To obtain uranium, they excavate 500 meters underground at this site in northern Saskatchewan, a province in western Canada known for hosting some of the largest and richest uranium deposits in the world. The extracted uranium is primarily used as fuel in nuclear reactors to generate electricity. This mine is the world's largest source of high-quality uranium. The uranium ore lies beneath a layer of sandstone saturated with water. To reach it, they use tungsten carbide drills like knuckles on a fist. The drills bore into the rock face. These initial holes are for tubes that will extract heat from the ground and freeze it around the ore. The miner operates the equipment remotely, transferring a new piece of pipe to the end of the drill every meter and a half to penetrate 130 meters into the sandstone layer. It takes up to 8 days to install just one length of pipe, and there are 200 of them. They set up the pipes to surround the ore deposit. These freezing tubes will stabilize the soil and also turn the high-pressure groundwater into ice so it doesn't interfere with mining. A freezing plant above ground cools the calcium chloride brine to minus 30 degrees Celsius and distributes it through the freezing tubes. The brine absorbs heat while freezing the soil and refreezes above the uranium deposits. Now they are ready to extract the ore. They will use this drill to bore into the ore body and make an initial small diameter hole, known as a pilot hole. The pilot hole traces the drill's path to the ore and creates an entry point for larger mining equipment. From an elevated position, the drill vertically bores into the rock to reach a specific level below the ore body. Now they're ready for the reaming drill. The drill lifts the reaming bit through the pilot hole, lightening it. A remotely operated cart picks up the rock. This remote control system keeps miners at a safe distance from falling rock hazards. It also minimizes their exposure to radioactive uranium in the ore. As an additional precaution, they continuously ventilate the mine by introducing fresh air every 20 minutes. Operated by the operator's control lever. The cart delivers the ore to a scanner. By measuring the amount of radioactivity in the ore, the scanner determines that the uranium content is approximately 15% in much of the ore. The uranium content is even higher, on average around 18%, and that is considered very high quality. The cart now empties the ore into a chute from a control room. An operator manipulates a hydraulic hammer to crush the ore into pieces. The crushed ore is distributed to a mill that grinds it into a fine sand. They then add water and it turns into a slurry, which is then pumped to the surface. Trucks transport the uranium slurry to a mill 80 kilometers away. They stop at a special unloading facility. The vacuum system support lines up with the container enclosing the uranium tank. Once in position, a vacuum tube drops into the tank and sucks up the slurry. After washing and radiation checking, the truck leaves the facility. The powdered ore is treated with acid to obtain uranium. The uranium slurry is fed into large tanks filled with acid. The acid dissolves the uranium but not the rest of the rock. The rock settles to the bottom of these tanks. The uranium acid solution flows forward, leaving unwanted minerals behind. Using a series of chemical reactions, they further purify the uranium. They then heat it to 850 degrees Celsius. First, the uranium is converted into gas so that uranium-235 can be enriched, which is the isotope needed for a chain reaction. This gas is fed into centrifuges, where centrifugal forces are used to separate the uranium isotopes based on their mass. Uranium-235, being slightly lighter than uranium-238, concentrates more in the center of the centrifuge, allowing for its separation. Once separated, it is concentrated into a black powder like coal. The uranium powder flows into 210-liter steel drums. The drums are then shipped to a nuclear fuel processing plant. The uranium goes from black to yellow as it is converted into uranium trioxide, an intermediate chemical form in the processing chain. They send the uranium trioxide into specially designed inverted cones upon arrival at the facility. A valve opens at the bottom, and the powder flows into conveyor tubes that carry it to the plant. Inside, they dissolve the uranium trioxide powder in acid. A worker takes a sample to test density and chemistry and confirms that both are acceptable. They then add a chemical to convert the dissolved uranium into solid form. After further processing, the uranium trioxide becomes uranium dioxide, the required chemical form for nuclear fuel. By centrifuging the uranium dioxide, particles of different sizes are mixed to make a more homogeneous blend. The chemical processing has also changed the color of uranium. Now it is a fine black powder using several tons of pressure. Presses mold the uranium dioxide into pellets. A rotating wheel with protrusions guides the pellets onto a channel conveyor. A uranium pellet the size of a peanut generates the same amount of energy as 800 kilograms of coal or 560 of oil. The conveyor carries the pellets to an oven for 24 hours. Heat removes the pores from the pellets. The pellets shrink, increasing the density of uranium. A robot arm loads the pellets onto a tray and levels them. The conveyor moves the tray forward. A robot places zirconium fuel tubes on a rack. Zirconium is a metal highly resistant to both heat and corrosion, but neutrons will pass freely through it during the fission reaction. The tube rack meets the incoming pellet tray. A robotic loader pushes the stack of 30 pellets into the tube. The pellets are placed inside metal tubes which are then assembled into fuel assemblies that go into the reactor core. The tubes pass one by one to an automated welder that caps the ends. The next robot retrieves the completed uranium fuel rod and transfers it to an assembly device. After the rods have been welded and the assembly has been capped at both ends, a robot transfers it to a scale. This scale confirms that there is the correct amount of uranium in the assembly before it is burned in a reactor. The amount of radioactivity emitted by the nuclear fuel bundles is very low, and they are safe to handle while workers prepare them for shipment. This nuclear fuel is packed with enough uranium to power 100 homes for a year. The fuel is received at the nuclear power plant, where it will be inserted into the reactor core in the nuclear reactors. Uranium serves as the trigger. It acts as the initial energy source for what eventually becomes electricity. Each of these bundles of uranium fuel produces enough heat to generate 1 million kilowatt-hours of electricity to bring them to life. They must be inserted into the reactor core. The 480 reactor tubes can each contain up to a dozen fuel rods. And when the 5760 rods are in place, the show begins. Nuclear fission converts matter into energy that is released as huge amounts of heat. Some of the uranium atoms within these fuel rods are excitable, and when excited, they start releasing neutrons in all directions. The tiny neutrons can pass through the zirconium walls of the fuel rods, flying from one tube to another until they collide with another uranium atom. When they do, the atom splits, releasing energy in more neutrons, and thus a nuclear chain reaction is obtained. But when it accelerates too much, it needs to be stopped. If what scientists call a nuclear reactor meltdown does not occur, the reactor is not only sealed between 2-meter-thick reinforced concrete walls but also automatically shuts down if the temperature rises or the pressure drops too quickly. The heat is used to convert water into steam, a process carefully controlled from the control room of the plant. The huge turbines placed in a 400-meter-long room and 20 stories high convert the steam into electricity. The turbine spins at 1,800 revolutions per minute and powers a generator. The gigantic generator wheel converts the motion into over 750 megawatts of electricity, enough to meet the needs of 500,000 people. After about a year in the core, the fuel bundles are spent, but they are also extremely hot and radioactive. They are so hot that the rods must be stored in water for 10 years before they can be safely disposed of. They are placed in a pool at the plant to cool down and for the radioactivity to dissipate. Sunken in the depths of this 8-meter deep pool are over 700,000 radioactive fuel rods. Like the video if you enjoyed it and share it with someone who might be interested. Also, subscribe to this channel by enabling notifications to keep learning.